the last video, we left off with the following model for our three-phase AC synchronous generator, where we had placed our field windings on the rotor and our armature windings on the stator. Then we saw that we needed a DC current for our field windings that we have placed on the rotor. Now we are going to discuss that how can we provide this DC current without using any carbon brushes or slip rings. Well, the basic idea for doing so leads us to a kind of a special circuit that is called an exciter circuit. The basic idea of the exciter circuit is to imagine this placement of our field winding and the armature windings in reverse. And so you can think of this as we want to place our armature windings on the rotor, and we want our field winding on the stator. And so we will also need a DC current for this new field winding. DC current. Now if the rotor is rotated inside the stator and we have a DC current flowing into this winding, this new field winding, then we will have a magnetic field B. Let me call this BE. E subscript is for the exciter. This BE will be controlled by its own DC current IE. Let's call this current IE. If this IE is controlled and the rotor and this BE is also directly proportional to the current IE, and the rotor is rotating inside the stator, then I will have three-phase voltages induced on the armature windings, on these new armature windings. This new circuit that I have just added into my three-phase AC synchronous generator is what is called the exciter circuit. This is our exciter circuit. Since the voltage is induced on the armature of the exciter circuit are three-phase, we would need a three-phase rectifier at the output terminals of the armature of our exciter circuit, and the output will be a DC which we can simply provide as input to our field winding, the actual field winding that we have placed on the rotor. So you can see that now, since now we have this new variation in our design where we have placed another generator inside our three-phase AC synchronous generator, such that its armature is placed on the rotor, while its field winding is placed on the stator. And when the stator rotates, we have three-phase voltages induced on its armature windings, which get rectified and provided as DC. That DC current I is used for generating our rotating magnetic field pointing out from the rotor. Now the question is that how can we provide this DC current for the field windings of our exciter circuit? Well, let's assume that we are working in some environment where three-phase voltage sources are available, small three-phase voltage sources. So what we can do is simply place a three-phase rectifier like this, get a DC output and provide it to the field winding of this exciter circuit. So now when the machine will rotate, we will have our own rotating magnetic field on the field winding of the rotor that we can use to generate three-phase voltages on the stator. Now all looks good, but we also said that we want to control this magnetic field, rotor magnetic field, using some current so that our induced voltage is directly proportional to not only the velocity but also the magnetic field. Well, that is quite simple to do. You can place a resistor in this path of the DC current of the field winding of the exciter circuit and make this resistance variable. By changing this value of the resistance, you can control IE. If IE is controlled, then BE is controlled, and automatically BR is also in our control. Now, as some final comments on the three-phase AC synchronous generators design, we want to say that what if we don't want any other input than the mechanical input for rotating the rotor? we do not want to provide any kind of three-phase AC to our machine, and we only want that we rotate our rotor and we have three-phase voltages induced on the stator. Well, we can simply do that by placing another small generator inside the machine. Let's say its armature will be placed on the stator this time, and for the field, for its own magnetic field, we will use permanent magnets like this, permanent magnets. Now you can see that the permanent magnets have been placed on the rotor and its own armature is placed on the stator. This third half of this third part that we have added into our circuit is called our pilot exciter. Pilot exciter. Let's see how this complete machine operates. Well, as soon as you rotate this rotor inside the stator, the magnetic field of the permanent magnets, let's call this BP, will induce three-phase voltages on the armature of the pilot exciter, which will get rectified from this three-phase rectifier. The output will be a DC, and this DC current will be controlled by using this resistance. Since this DC current is on our control, then the magnetic field that is coming out of the field winding of the exciter circuit is also in our control. Which will be used to generate three-phase voltages in the armature winding of the exciter circuit. These three-phase voltages will again get rectified from this three-phase rectifier, and finally a DC current will be given to the field winding, the actual field winding of our three-phase AC synchronous generator, and this BR will be used to generate the three-phase voltages at the armature windings that we have placed on the stator. Since BR is variable according to the current IE, and IE is variable according to the resistance R, we have this BR in our control. And now we have a magnetic field BR that is also variable. So BR is directly proportional to the current I that flows into it, and this I is in our control, and hence we can say that our induced voltage will depend not only on the velocity with which we rotate the rotor, but also the magnitude of the magnetic field. This wraps up our discussion on the design of the three-phase AC synchronous generator. Thank you very much, and see you next time.
Good.